Okay, so for this lesson, we are going to talk about 403. 403 is talking about using elementary matrices to act on the columns. Okay, and so there are basically two main ideas in this lesson. And the first one is very easy. Whenever you have an matrix A, you can write it as the column vectors, right? It's a collection of column vectors. We did this all the time, and suppose we have a matrix. You can think of that as an elementary matrix or whatever. If E is a matrix that is multiplied from the left-hand side, then E times A is equal to E times each columns. Okay. Okay, so if that is okay, then the next thing is we're going to think about what does it mean by multiplying an elementary matrix to a column. Give me a second. Okay. So now the takeaway for this one is that the matrix E will perform a transformation on each column. And here is what I mean. Just an example. Let's say I have a column called U1 and it is 2, 2, 1. Alright, and then I'm going to multiply this column by an elementary matrix which is called E. E is equal to 5, 0, 0, 1. So after the multiplication, you get something like 5 multiplied by the first coordinate, and then second coordinate does not change. After all, this action is saying first row need to be multiplied by 5. So U1 becomes 10, 1. A bit long. Let me do that again. It is a bit longer, but the height is the same. And say, suppose we have another vector called U2. U2 is 1, 3, just like the handout we had. Then E times U2 is equal to 5, 3. Again, the height is supposed to be the same, and then you got E U2 is equal to 5, 3. So if you have some shape that is spanned by these two vectors, then the shape will also be changed. and becomes something like this. And this action is basically saying you are stretching the canvas or the plane left and right by 5 times. So whenever you have a picture here and you apply this action to all the vectors on this place, then it will stretch the whole things left and right by 5 times. And now you see that this is like an action that we have been doing for images. For example, 小画家, right? You can do something like this. Even here, you can perform this action. Can I? Okay, it looks like I cannot do this for this one. You see, if I have a circle here, then many app allows you to do this action, right? And so this is 1, and then you have a 2, 3, 4, and even 0 is okay. Not for this app, but this is -1, -2, -3. So you can use the scatter to change the x coordinate. You can rescale the x coordinate. And so it turns out that every elementary matrix corresponds to a certain action on the plane. So let's see what's going on here. Okay, so let me just draw a picture and then see what I can do with it. I have an origin. Let me put an arrow on the 45-degree, and let's say this is a picture of a person, although it looks a bit weird. Let me group it and then make several copies. So let me give you some example of what things will go on. If you do an operation, this is 0, 1, 1, 0. And this action, you know what does it do? It is changing xy to yx. So what it did is the swapping x and y axis, and basically you are reflecting along the 45-degree line. So what happens here is you have this one, and let me see if I can do that. For this case, let me just draw it. So if you have this person and then you got the origin here, then you still get the origin. And you're going to do a 45-degree rotation, reflection, and you know the arrow is probably also still on the 45-degree, so it does not change. But the head was here, so the head will becomes here, and you have this is on hand is on the other side, and you have the leg. So if you perform this action on the plane, then x and y will be flipped. They will change their role. So this is the action 1, right? And we often do this by row I and row j. We want to swap their action. And secondly is you can do something like a 2, 3. If you perform this action to xy, then it becomes the 2x and the 3y, which means the x x direction will be rescaled by 2, and y direction will be rescaled by 3. And this one is easier to be done by this app. So what happens is the origin is not going to change, and then the x direction will be rescaled by 2, and the y direction will be scaled by 3. So it becomes 3 multiply its height, but the width is the 2 times its width. So this action is called rescaling. We often do this. It is done by rho I is equal to rho I multiplied by a certain scalar. So the last one is the action that is multiplied by one row multiplied by a certain scalar, and then add it to the other row. And for example, if I do this, okay, if I have xy, then it becomes x plus 3y. And this requires you to have some imagination, okay? So imagine that you got a box here, and origin is at the center. Okay, this means that the y value is going to be the same, but the x value is going to change according to y value. So what happens is, the more going up, the x will go to the right a bit more, and in the end it becomes something like this. I make it a bit bigger, but y is supposed to be the same. Okay, so y stays the same. This line becomes this line, but everything is shifted to the right because the y is a positive value. And this line is equal to the bottom line here, and it is shifted to the left because y is the negative value. In this operation, the transformation is called slanting. Slant 就是倾斜的意思 okay? So you will make this picture slant to the right a little bit, and you can still draw the picture. This is supposed to point to the vertex, and you got the picture here, you got the head here, but everything is distorted. Okay, I'm not doing a good job, but I hope you get the idea that everything is moved to the right a little bit. Okay, but let me do something about here. If you have some shape here, you can imagine that its area will be multiplied by k for the second case. This is the easiest, right? If you multiply by 2, multiply by 3 for the 2 direction, then in the end, the area will be increased by 6, which is 2 times 3. And for this one, the height is supposed to be the same. As I mentioned, sorry, this is supposed to be the same. Okay, the height is the same, and also your width is also the same. You just move the width and then slant it a little bit. And so it is still width multiplied by height. You know, 平行四边形 parallelogram, the formula is the same as the rectangular. So this is basically staying the same. The area, it does not change. And for this one, it is basically staying the same, but for some reason, we will add a negative sign to that. We will explain that at some point, but you just keep it in mind that when we flip the order of x and y, then when we count the area, it is a bit different. Okay, so this sort of giving you a sense that if you perform different kind of action on the columns, then it will be multiplied by -1, k, and 1. So let's get to the summary of this lesson. For each matrix, we can consider something called parallelotope, column parallelotope. Okay, for your for comparison, you can check for polytope. Polytope means 多面体, and parallelotope means certain kind of 多面体. Okay, and let A be a matrix. Any matrix, a square matrix. And this object, parallelotope, is the following definition. It is a set. It looks like this. C1U1 plus everything up to CNUN, such that for each I is between 0 and 1. This means that Ci is between 0 and 1. This is an interval between 0 and 1 for each I. Alright, it's not so easy, and at the beginning when you see this, it's not so easy to think about what's going on here, but it will be easier to think about what is 0U1 and what is 1U1. Okay, say this is U1, right? So what happens is, basically here means that C1 equal to 0, and here means that C1 is equal to 1. Let me write that again. C1 is equal to 1, and C1 is equal to 0 for this place, right? So you are moving along this direction, but you cannot exceed U1 itself. Now, suppose I have U2, and you also have something like here. This is C2 equal to 0 up to C2 equal to 1. So any linear combination using these coefficients will give you the origin U1, U2, U1 plus U2, and everything in the middle. So in the case of two-dimensional things, then you will get a parallelogram, including the boundary actually, all the things. This is called the column polytope, column parallelotope. Okay, so I'm going to define the volume of this one and using the matrix. The side volume it's a new term, but it's a volume, but sometimes we will give a positive or negative sign. Volume C of the column parallelotope of A is defined by the following rules. Rule number 1. If you have the identity matrix, and you can imagine what is the columns of an identity matrix. It is the standard basis of a space. So for example, you have E1 and E2 here, right? E1 and E2 here. What is its parallelotope? It is a cube. It's a square for 2 dimension. It is cube for 3 dimension. And in general, it is a 1 by 1 by 1 block. So for IN, the volume of that is equal to 1. And you can imagine that it is just 1 by 1 by 1. It is a block. It's a very fundamental thing. And then, secondly, we can use all sorts of actions that we learned in the previous page to perform something. If if you swap row I and row j in A and obtain B, in this case, we will say the volume of A is, the volume of B is equal to the negative of the volume of A. And it's kind of not intuitive, but it's changing the orientation. Orientation in mathematics is kind of a direction. The easiest example is you heard of 左旋蛋白质 and the 右旋蛋白质, and that's kind of it's saying that this is following different orders. So x and y and yx, this is different things. Now the other two actions, we can apply another row operations to A, which is row I, becomes row I multiplied by k. If you do this and then we see by the previous things, B will be, the volume of B is equal to k times the volume of A. And this is really just a rescale. 伸缩. The last one, if I start with A and then perform the row operation by row I is equal to row I plus k times row j. If you do this, then it is a slanting, then the volume does not change. Okay. So with these rules, I claim that every volume can be calculated in this way. Later on, you can use the experiment part of this handout 403, and you can see some concrete example in two-dimensional plans. So definitely, please check out the pictures there and see what's going on. So let me pause the video.